Okay, like I said, we'll go ahead and get started here. And
I'm so excited.
if you are tuning in, you might want to leave some space in between. And we're just talking about these compounds here. None of that material over there, just these, and then leave spaces between those. Because this is somewhat of a review, we could say, because we've been spending time with talking about electrons, and of course this is no different. We're just not doing Bohr models or orbital diagrams or anything to that nature. We are illustrating different types of bonding that happens within these compounds. Some of these are covalent, some of these are ionic, and some of these are polar covalent bonds. Okay? So would you just like to go in the order that is preceded, or
Yeah, I think
what works best for you?
Polar what?
Polar covalent.
Great to start at the top.
Okay? So then, with each and every one of these elements, with the exception of metals, what rule might we be trying to satisfy? And we read about it yesterday, the octet rule. So that means that some of these atoms are going to have 8 dots or triangles or X's or whichever around them. Some of them will not. Okay? So maybe we should start with that. What are some elements that will not have 8 around them?
Hydrogen.
It would have to be hydrogen because it only has 1 electron.
Potassium.
And if hydrogen doesn't, well then potassium won't. But not for the reason that you might think. It's +1. So what do these two elements have in common, though? They're in the first column, so that's really important. Okay? So then, as we start this, you want to locate where they're at and what column they're in, because when you locate the column, that's telling you something very specific about that when it comes to the dots, triangles, X's, E's, or whatever.
It's how much it has. Like how much
Yeah,
dots it
how many
has.
valence electrons. So what we mean by that, now, you've done this probably 15 times last chapter. So if you want to write it down, fine, but this is what we're talking about. We've got 7 protons inside of there. So that means we've got 2, okay? Then we've got 2, and then we've got 3, okay? So the numbers on the outside correspond with what's on the inside, correct?
Yep.
So 3 plus 2 plus 2 equals 7?
Yep.
Yes, it does. But that maybe doesn't help us with the nitrogen other than saying, here is our outer level, right here, and how many do we count? How many electrons?
5.
So what we see that being based off of, we just shown you with the Bohr model. Otherwise, when we count left to right, okay, here's nitrogen right here. So column 1, column 2, we skip the D block, so column 3, column 4, and then column 5, okay? So therefore, that's where this 5 comes from, okay? And of course, we could break that down even further. We could say that it's in the second period, nitrogen is, okay, which includes these 2 blocks, and then it's in the 3rd column of the P block, but in the 5th column of the entire energy level. So therefore, we start with our nitrogen, and how would you like to denote those 5 valence electrons?
X's.
Okay. Live in Texas, right?
Yeah. Oh, not X.
I didn't know if anyone would know that. George Strait. And
X's.
What early?
Is the blank.
Class
You listen to George Strait?
I haven't listened to George Strait, but I've listened to.
Okay. So with this, okay, typically you just want to try to get 2 electrons in each side, and that's fine. But what do you suppose you do with electrons that are not being shared if they're all by themselves? You keep those together. This is what we mean. So you said X's, okay? So 1. Now, you can go ahead and do 2 right away and then go around, or you could say, well, I know I need to do 5. Just do 1, 2, 3, 4, and this kind of follows the bus seat rule. Then you have those 2 up there. Those are our 5 valence electrons.
Does it matter where they're at? Or could it be like 2 X's on the right side?
Yes, you could do 2 X's on the right, then 1 on the bottom, left, and top. That would be fine. Okay.
Could one be on the bottom, right, bottom? You could put them anywhere.
Okay, whichever. If you want to have 2 there and like that, that's fine. If you want to have 2 there, and then you can do it like that. That's fine. But the most common place would be this. And then we've accounted for our nitrogen, and then we have 3 hydrogens left. And as we correctly said, hydrogen's in column 1. Therefore, everywhere that there's an X, we make a single bond. And that nitrogen now has 8 electrons around it.
Whoa.
Is it stable?
Yes.
Okay.
Yes.
Does it have a charge?
No.
No, it does not.
Yes.
Okay. So one of the things that you'll probably be responsible for in college when you take this is knowing the geometry behind it. And that geometry, I believe, is at 109 degrees. So what does that mean to you? Because these electrons are not shared up here, that's why you keep them together, that this molecule really looks something like, oh boy, I think it's between these 2 is where, and that's where this angle is about 109 degrees. But for our level, for our purposes, we're not concerned about that. But I think if you hear it once, if you hear it here, you say, oh, I remember that maybe short conversation. You might not. Okay? But that's where that comes from. And then everything is satisfied. The hydrogen doesn't have 8 around it, but it doesn't because it doesn't have that capability because it only has 1 electron. So you got to keep that in mind then.
So the hydrogens are filled, its outer energy level is full because it's taking 1 from the.
The hydrogens, no. The nitrogen is.
If all it can hold is 2, then it has 2.
Oh, you mean they're being shared though?
Yeah.
I interpreted that you meant completely transferred to it. Okay,
That's why it's
yeah.
still stable.
That's why it's still stable. That's right. Okay? And then that is why this, we said we've got covalent bonds, we've got polar covalent bonds, and we've also got the most common one that you probably like to do the most. Okay, I want to make sure. Did you say bionic or ionic?
Ionic.
Oh, that's why. Okay, I thought I heard bionic. I said, well, you're not too far off. Ionic bonds are probably the ones you're going to like to do the most because those seem to work out the easiest. You don't have to worry about different types of multiple bonding taking place. Each and every one of these is going to be single bonded though. Okay? So that's one thing that does make this easier. So regardless, this is still we do want you to know this. It's a polar covalent bond.
What makes it?
Alright, I'm gonna write that down.
So the one on top is a polar covalent bond. The NH3.
No, this whole molecule is a polar covalent. That's why. Because you have two unshared pairs, well, not two, you just have two electrons that are not being shared or transferred or anything like that.
So the ionic bonds are so,
We haven't got that far yet.
I know, but it's just so stupid.
Yes?
What's the one on the top?
This one here?
Yeah.
We just wrote it down. It's right there. All right. So then when you're doing these, I think it's fair to say that there's an order you want to proceed, or would you call it a hierarchy, order of procession? Just say there's probably an order you're going to want to go through. And that is, if these two elements are present, you're probably going to want to start with either one of those. Okay? Then you would proceed to perhaps the non-metals. Okay? Well, what happens if you have all non-metals in there? And we'll finish up with that a little later. So I want you to pick phosphoric or sulfuric.
Sulfuric.
Okay?
It sounds good.
We'll come back to this and we will actually end with that. Okay. So moving forward then, as we look at this one, okay, we got KBr. We don't have carbon, we don't have nitrogen, but looking at these two, how do you tell the difference between potassium and bromine?
Bromine's a halogen.
It's a halogen, so where's it at on the table?
Seventh column.
Okay, and that's really specific, which is fine, because you're not going to go wrong with that when you say the halogens in column 7. The point being, they're clearly on the right side of the periodic table. Okay, so what do we mean by this? Here's your table. They're clearly on the right side with the rest of these halogens. Where is potassium located?
On the way left side.
On the way left side. And what do we know about those in yellow? Going all the way back to the left. Those are all specific. You can handle most of these. They're all metals. Yes, sodium, potassium. Those are metals, even though they're highly unstable. You don't want to store these in water. You'd have to store them in something like probably kerosene. You could probably store them in gasoline or diesel, something that's stable, that it just doesn't have the ability to react with air. This here, it won't rust, it'll explode. Okay? Okay, so which element are we going to start with?
Bromine.
And why would that be?
Because it's
Yeah, because it's a non-metal. Okay? And then how many dots, X's, triangles? Okay?
7 X's.
How about hexagons?
And we'll just try to beat us to the punch. If you can put 2 of them over here and leave 1 up there.
Yeah.
Okay? You can put 2 of them over there, take 1 off here. It doesn't matter. It's just that we read left to right, so it just makes the most sense to do that.
Yeah.
So then bromine wants how many more electrons?
1.
Okay? And it's going to get that from the potassium.
Just 1.
Okay? So this has no electrons around it at all. It's not being shared. it completely got transferred to this bromine. Okay? All right. That is a metal and a nonmetal, making that an ionic bond.
Like if you pay attention, you know.
Just double check. How do you know if it's a metal? Is it like the yellow on the left?
It says it on the periodic table.
It says it, and we had said if you go from the yellow going all the way back to this side, the majority of them are safe to handle. Okay? Especially the ones in yellow, these metals you can pick up and you won't have any issues with that. It's these in here, the alkali metals and alkaline earth metals. You gotta be a little careful of those because they're not quite stable and safe to handle because they're in columns 1 and 2, and they will lose their electrons fairly easily then. All right.
Okay, so the green in metals and
The green, yes, those are metals, and the blue is metalloids, and yes, I think this got cut off, but yes, it does have a key on the bottom. Okay,
what's a metalloid? What's the difference between those two blues?
One's lighter, one's darker.
Yeah, one's lighter, one's darker.
But where's
Okay.
the dark one on the
all right,
It's on the right.
okay. So then, with this one, okay, if you really, really, really wanted to be specific, this is more so of we call it a polar covalent bond as well, and it probably makes more sense to classify it like that, and I'm going to show you why here in just a moment. So which element would we start with?
I don't know.
We're joking, right?
You would start with F. Fluorine.
I like
Why are you right?
It's a non-metal.
It's a nonmetal. I mean, we're not talking about New Mexico here, all right?
Yeah.
So start with our fluorine, column 7. Now,
More than before.
you tried it, and I probably didn't draw that very neatly either. You just try to keep 2 of them on each side so that you can just go through, okay, 2, 2, 2, and 1. That gives us 7. Here is our last one. And this more so relates to that table that we were looking at yesterday, okay? Or no, that was in the organic class we were looking at that, okay? But what happens here is this electron is getting pulled in closer to here. It's a complete transfer, or excuse me, it's not quite a complete transfer because that is, again, is resonating back and forth. It makes this what we call a partial negative charge, this a partial positive charge. Same thing up here. What are we repeating?
What's it mean?
Okay? So it doesn't make any sense to me either. Okay? So this also is a polar covalent bond. Okay? All right.
Isn't a metal and a non-metal ionic?
Typically, yes. But here, this is a complete transfer. This is pulling this in closer, making that partially negative and that partially positive. That only happens because this is not a clear metal. It's a gas, okay? But that we do want you to know. If it's a metal and a non-metal, yes, you can say that is ionic. So when we have these differences here, we still want you to know this is being a polar covalent bond. Because it's hydrogen. And you see these in there. That's right. Okay?
I don't have a red color. I only have like a pink. It's up there.
Okay? And then this next to last one, which element would we possibly start with?
Carbon.
Okay,
Secret. Carbon. I started with carbon.
I would start with carbon.
I guess, yeah.
Okay, so, and I'm presuming that you two didn't guess over there.
No.
I think
Okay, and that is how did you know it was carbon?
You told us.
Yeah. You got this hierarchy right here. If carbon or nitrogen are present, probably want to start with those. If you have nonmetals, when those are not present, you probably want to start with that. And then this is something that we'll get into later. Okay, so what you probably want to do when it comes to these organic compounds, this is a covalent bond because they're just being shared equally. That doesn't take place with this. Again, because that is hydrogen. Okay, so we start with our carbon, and it's in which column? It's in which column? Okay,
I'm at fourth. Oh my God.
all right. So we would go ahead and put those 4 valence electrons. Then what we want to do is create a bond.
we gotta write this down.
Okay, so then we've taken care of 1 carbon. We still have 1 left. So what we would do is do a progression on, are we going to do single bonding with carbons? Are we going to do double bondings? Or are we going to do triple? Because carbon and nitrogen can both do that. They can single bond, they can double bond, and they can triple bond. So it's going to be single with this. The reason being is we're going to do our other carbon now, still in column 4. Okay, so we've got our single bond. These are being shared equally with each other by creating that bond. Now you can pick either your hydrogen or your chlorine. It doesn't matter which one. Okay, so where would you like that chlorine to go? Okay, and we can put that chlorine atom here, and we'll go ahead and make it a different color since we have so many different elements on here. And then what column is that in? Okay,
7th one.
so we can go ahead 2, 3, 4, 5, 6, and 7. Okay, now you're going to look at these carbons and say, this one's only got 6, this one only has 5. Is that a problem?
Yeah.
It is right now.
Yeah.
So how would we go about finishing that? Because we haven't dealt with which element yet.
Hydrogen.
We haven't done the hydrogen yet. Okay, so how many hydrogens do we have?
5.
Okay, so how many places is there a possibility
5.
to bond? We have 3 X's and 2 triangles, and then now we're back live. Okay, so everywhere that there's a triangle or an X, we're going to go ahead and put a hydrogen, and we'll just go ahead and do E's. Okay. Have we accounted for each element?
I think so.
Okay, with the exception of hydrogen, is there an octet around each other element? So this is something that you would have done 2 years ago, and until you get a really good understanding of this, you might think it's easier to know and draw this out as ethyl chloride, because that's really what we're drawing, or chloroethane, whichever way you want to look at it. Since this was our formula, if you remember from physical science, there's our single bond that we just shown, okay, between here, all right? Then there's our 5 hydrogens.
Bet you $20 to have that written in my notes.
And then there's our last single bond. Because remember, if there was nothing written on these carbons, you would presume that those are hydrogens.
You already told me to shut up.
Okay? Then what you're doing is, here we had a triangle and an E. Here we had a triangle and an X. Does everyone see the pattern that we see coming around here? Down here was a triangle and an E. You're doing the same thing, but you're just using dashes instead of the triangles and E's. Until you get a really good understanding, I would suggest that you do this. You might say, gosh, this looks so much easier. And to some people, it might be. Because now what I want you to look at is something like this. We'll do that.
C2H10.
You probably want to start with your carbon. And now, in my mind, I think that's right, but that's why we're practicing this. Okay? So you have this, carbon and nitrogen are present, so we're going to go ahead and start with that carbon. And then the progression that you're going to go through is that, notice we started with a single bond, and it worked. That's not always going to be the case. Okay? And maybe this will work too.
What kind of bond would you call that? The C2H5.
What kind of bond is this?
Yeah.
Just single.
A single one.
Yep.
Well, like, you know how the other ones are ionic bonds and the other one's polar something. What kind of?
Oh, okay. These are actually tetrahedral.
How do you know that?
Tetrahedral.
Experience.
But we need to know this for anything else but this.
Well, we wrote it down, and no, you don't need to know this. Okay.
I was gonna write it down.
All right. Okay. So we'll go ahead, and that might, like I said, that might not be right either. We're trying to shoot from the hip, just seeing if this would actually work out. So we're going to try a single bond.
It doesn't. Yes.
Okay. So here is our single bond with that carbon. There is our single bond with this carbon. Okay. So we've got a hydrogen, and then even you put a nitrogen here, none of that's going to work. So single bonds is not going to work. We have 8 around this carbon, but then notice this one only has 6. No, sorry, it only has 5. And this one doesn't have 8, it only has 7, because it has a lone electron down there. So if a single bond doesn't work, what might you try next?
Double.
Okay, so what you're doing, okay, is this between your carbons, and those are just horizontal lines. Okay, so this one, we go there and there, that takes care of this carbon. We go here and here, and that takes care of that carbon. Okay. I don't know yet. We have a hydrogen, we'll put that here. And then we could put maybe a nitrogen makes a single bond down here. Okay, so 2, 4, 6, 8. This carbon has 8 electrons, but this one only has 6. 2, 4, 5, and 6.
So you need a triple bond.
Okay, so let's try a triple bond then. Okay, and then, so let's try that. So then what you're illustrating here again is triangle, 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 X, X, X. So what do we have over here? We have one X left, correct?
Yeah.
So could we put a hydrogen here? Okay, that takes care of that carbon. Then this one still has one left. So the only place we could try is here. And how many electrons are around nitrogen? How many do we do up here? 5. So let's try a single bond here. Okay.
I tried double bonding and I think it'll work if we have one more hydrogen.
And that's just it. I think but we got to be careful about this. We've got 6 and 8, 6 and 8, so both carbons are good. One, 2, 3, 4, 5. Okay. Then what happens is we're still
Kyle, why are
short.
you looking back at me? Pay attention.
Okay.
Because you keep making comments and it's annoying.
It's a question.
Then raise your hand.
Why are you
Okay.
looking at me in the first place?
So
Thoughts are really wrong.
I think that concludes today's lesson. So we'll pick up with this tomorrow.